Good morning, everyone, and welcome to our second day of press conferences at the EGU General Assembly. We start today with a press conference on the consequences of nuclear accidents, Fukushima and Europe. And I would like to remind everyone that after short presentations by the three speakers, we'll open the floor for questions. We'll give priority to the journalists here in the room, but you can also ask questions if you are watching us remotely by messaging on Skype EGU.media or by using the Twitter hashtag AskEGU. So I'll introduce our press conference participants now. We'll start with Professor Yushi Onda at the Center for Research in Isotopes and Environmental Dynamics at the University of Tsukuba in Japan. Professor Kita, who is at the College of Science at Ibaraki University in Japan, and Professor Petra Seibert at the Department of Meteorology and Geophysics of the University of Vienna. Professor Onda, you can start.
Okay, and thank you for coming to this meeting. So my name is Yuichi Onda, University of Tsukuba, Japan. So after the accident, nuclear power plant accident, Japanese government funded our group for the environmental transfer studies beginning June 2011 to March 2014. So our group is a kind of large group, university group, and so try to evaluate every aspect of the environmental transfer of Fukushima-derived fallout radionuclides. The atmospheric part, the suspension, has been done by Professor Kita, and the other part is working with the colleague at Nagoya University and our university and Kanagawa University, who have low-level activity radionuclide materials, and Hiroshima University and Kyoto and Fukushima University and Chiba. And our study is focusing on every aspect of environmental transfer. And the first things we should focusing on the study of environmental transfer in some research area. The research areas here in Yamakia area in the Kawamata town in the evacuation area. So the fallout cesium inventory is ranging from 300 to 1 megabecquerel per square meters. So, okay. So we have several stations in the study area, try to evaluate the processes from forest to land and erosion part and the groundwater and stream water and some resuspension stuff. So the first we start research and distribution and migration in the forest using the tower, and also try to collect a sample from fallout data and water. And then we study the transfer of radiocesium by the soil erosion. So for that purpose, we established the 5 points of erosion plot in this area. And this is the soil erosion plot looks like, and try to evaluate the several different typical land use and try to use this data for the future modeling. And then also there is a particular land use in here is in the paddy field. So that purpose, for only this purpose, we have cropped the rice to evaluate the environmental consequence of the rice field to the streams. And finally, we measure the concentration of radionuclides with the river network. For this purpose, we have several stations, mainly in the Kuchibuto River station, and also the mainstream, including Fukushima City, and to the ocean to evaluate how much radionuclides flowing into the ocean. So this is just a summary of the data. Sorry, it's quite small, but So the first we study and followed the nuclide movement from the forest canopy to the ground. So at the initial period, the contamination level of the leaves is quite high, something like 50 kilobecquerel per kilogram. And then after the monitoring of 1 year, almost 1 year, the level of contamination is decreasing significantly. And also, so we have monitored the sediment movement associated radionuclide transfer, and we found that as much as 3.45% of sediment, radionuclides have been flown to the river associated with sediment particle. This is a very worst cases, but still have only 3% of the cesium have been flowing out to the stream. Even there is a quite big typhoon during this time. But in general, in most of the land use like grassland and forest, is only 0.2% of the cesium have been flowing into the stream. And we also measure the stream water and groundwater, but the level is quite low. The transport from the river to the ocean, there used to be very high level of contamination of suspended sediment. The year 2011, approximately about 60 kilobecquerel of the reservoir sediment is stored, and also the level of suspended sediment is the same orders. But after the 1 year, the level is decreased about less than half of it. So this project is still ongoing until 2014, until March, and we, our university group, try to monitor as accurately as possible to study the consequences of Fukushima-derived radionuclides. Thank you.
Okay. My name is Kazuki Kita from Ibaraki University, Japan. I'd like to introduce you about the activity of Japanese scientists to understand influence of the Fukushima accident on, especially in the atmosphere, in my specialty. So, in the Fukushima accident, much amount of radionuclide emitted from the nuclear plants, and widely transported in the atmosphere. By the wind, the radionuclide transported like this and diffused, and that during the transport, they deposited on the soil and vegetations. And after that, the deposited radionuclide may resuspension. Okay. So my first topic is the model study about to understanding of emission, transport, and deposition of radionuclide by the accident, and evaluation of the deposition amount over land and ocean. Yeah, this figure shows the measured surface density of radioactive cesium over at the end of the March in 2011. And these three panels shows the model calculation result example. More than 10 science group attended this intercomparison to reconstruct the observed surface density. By this intercomparison, 6 models in Japan and 4 models from Europe and America shows some there is some difference between the model and observation. That difference taught us the wet deposition process. Precipitation and fog is a major source of the uncertainty. So that this study of this process may be significant for understand how much the radionuclides distribute after the such accident. This shows several global model results indicating cesium total deposition at the end of March. These four models reconstruct the global feature of the cesium global distribution is similar. So our understanding roughly the deposition distribution is common. Okay, I move to another topic, about our observation, the variation of the atmospheric concentration of radionuclides from the accident and influence of resuspension. This map shows the sampling network by Japanese Geosciences Union and Japanese Society of Nuclear and Radiochemistry. Just after the earthquake and Fukushima accident, our scientists, Japanese several science team start such sampling network of atmospheric radionuclide. This is a bottom-up and frontier network, and there is no budget from the government at that time. Now we are supported. And we showed the result from these two sites, Fukushima City and Hitachi City. This is a time variation of the radioactivity density at these two sites. And this graph shows just after the accident, the concentration is about 1 becquerel per square meters and rapidly decreased. And before September 2011, the major source of the atmospheric radionuclide is coming from the Fukushima nuclear plant. For example, this graph shows some enhancement of the radionuclide, and for example, this peak shows this panel shows the model calculation of the plume from Fukushima nuclear plant. So at this time, the wind brings the plume from Fukushima to the Hitachi City, and this time the wind plume from Fukushima to the Fukushima City. Okay. And after September 2011, the leakage from the nuclear plant is become very small, and the major source of the atmospheric radionuclide is the resuspension from the surface. For example, now we are studying the, but you can see the atmospheric concentration fluctuated. Sometimes increasing and decreasing. We are now studying the mechanism of the resuspension of the atmospheric nuclide. For example, this is a wind is a significant factor to the radioactivity. Okay? And this is a distribution of the atmospheric nuclide in the aerosol, atmospheric size of atmospheric particles. Okay, our first topic, the modular simulation can roughly reconstruct the observed radioactive cesium distribution on land. But wet deposition process is a major uncertainty process to determine the distribution. So we have to study these processes. And model calculation enables us to estimate emission amount in the accident and deposition distribution, global scale deposition distribution over the ocean. And about the atmospheric concentration of radionuclides, atmospheric concentration of cesium and iodine was about 1 becquerel per square meters at the end of March, and significantly decreased after that. After the accident, before until September 9, 2011, leakage from nuclear plants is not negligible and probably major source of radionuclides. After that, the leakage is stopped, and the suspension from the surface was a major source of the atmospheric radionuclide. Thank you.
Yeah, hello. My name is Petra Seibert. I'm a meteorologist, and I will present some results of a study to you that we conducted in the past years about nuclear accident consequences in Europe, but I will also make some more general remarks, especially about emergency preparedness and response. And we could put all that under the title Lessons Learned or Lessons Not Yet Learned. We know that that is a kind of summary, what you see here. We know that some aspects of the emergency response at Fukushima have been unsatisfactory, and I will explain why and why I think it's kind of typical and it's associated with the lessons to be learned. We know that Fukushima was not the first severe nuclear accident, and maybe not the last one. We don't know. We hope not, but we cannot exclude that. So we have to wonder about the learning curve and why maybe not all the consequences that we could already have learned, for example, from Chernobyl, have actually been put into practice. Concerning our flex risk project, in this project we calculated consequences in terms of contamination and dose for hypothetical accidents in all the European nuclear power plants for 2,700 different weather situations. So we get a very good idea of what is the range of possible consequences. And some important conclusions are that basically all of Europe may be affected by an accident, and that severe consequences are possible beyond typical emergency planning zones. And on the other hand, if nuclear power plants were to be shut down in a region that is effective for the reduction of the risk of severe consequences, as that is like more regionally limited. Yeah, and the final point that I would like to stress is the issue of data access and generally prediction methods. So if we come to the Fukushima crisis, from my point of view of atmospheric scientist, what we can observe if we look at this contamination map that certainly you have seen many times, but I would like to ask you to look also at this line that I emphasized in pink, which is a little bit lower contamination level than the about 100 kilobecquerel, so that's still quite relevant. And you see it has a complicated shape. It's not just like a straight, simple line, and there are detached islands of contamination and so on. And also what we see, what you all know is that relevant or even severe contamination extends beyond these 20 and 30 kilometer zones. Yeah, and other observations that we can make is that there are dispersion models in place as part of nuclear emergency preparedness, but then in the crisis they were not used as foreseen, and the emergency response was still very much oriented to this concept of concentric circles and imposing measures just as a function of the distance. Yeah, and just I wrote as the last remark, iodine prophylaxis. I will come back to that later because it's also a very relevant measure. Yeah, I think that probably in most or maybe all of the countries that have nuclear power plants, we have a bit similar situation that emergency planning zones are basically designed as concentric circles, and also the most of or many of the emergency preparedness focuses on simple scenarios, simple accident, release, contamination, and so on scenarios. But typically these zones are too small for a really bad accident. And outside the zones, there is often not enough preparedness. For example, stable iodine tablets haven't been pre-distributed, so they might not be accessible when they are needed. Whereas in a country like Austria, iodine tablets are stocked in schools and kindergartens in the whole country. Already Chernobyl showed us some important features, namely that projected releases over several days with variable release strength are possible, and typically that leads to complicated contamination patterns. This here is an image of simulated deposition from Chernobyl over all of Europe. Here is like England, Italy, Finland, and so on. And that heavy contamination was found up to, say, 300 kilometers in Chernobyl, and a moderate one, if we use this terminology, like to distances on the order of 1,000 kilometers. So that shows us the scale where we need some preparedness. Yeah, and these here are just a sample of single cases of contamination that we found in our flex risk study to give you an impression of how different spatial contamination patterns could be, starting from a very simple one. I mean, still it is a heavy release and a large-scale contamination, which would go from France through Germany, Poland, but it's simple in shape. However, we can have many complicated shapes or maxima, like in this case, caused by wet deposition at the Dinaric Mountains here, where the air has to rise and heavy precipitation will fall, that are far away from the source. And the maximum close to the source here would be like on a small area and also mainly falling on the sea. And here you see then, you will see a movie on contamination of the air. You will see the movement of the plume. So you see it goes westward, then it turns around, then it moves different direction. Yeah, so making like very complicated paths, and it can go over one place more than one time, of course, which also like many emergency preparedness concepts don't consider, because they speak about 2-day dose or 7-day dose and think it will be just a one-time event. Yeah. Here on this slide you see a map of the risk originating from all the nuclear power plants in Europe for exceeding the thyroid dose that, according to the Austrian emergency plan, would lead to administration of stable iodine to children. And even though we see that there is, of course, a big variation geographically of that risk, a small probability exists everywhere in Europe. And especially like if we omit some parts of like Scandinavia and some parts of Iberian Peninsula and so on, like is really most of Europe is under a severe has the possibility of like severe consequences. Well, with this I come to the last point, namely what we can learn in terms of data and methods. Real-time data are really crucial, and such data exist on the state of the reactor, on the contamination. That means how much radioactivity is found in the air, on the ground, and so on, and on the dose rates. And this in local, regional, and global scales. And we have seen in Fukushima massive failures in monitoring, of course, partly due to the damage done by the earthquake, but also in communication. And we could observe that only the data from the CTBTO, the Comprehensive Nuclear Test Ban Treaty Organization here based in Vienna, were available promptly and to all the countries. But I think it is not so specific to Japan. I think if we would have the same in Europe, we would not be so much better off. I think all the web servers that would offer monitoring data, they would break down under the load, because we are not really prepared for information distribution in this situation. And also the formats are not really suitable like for us as scientists who could do evaluation, or even like say maybe you as science journalists who have a certain background. Maybe you would not only see the official bulletin, you would like to see some data. And then it's like, it's not so easy to manage all this data in proper way. Another important finding is that both in Fukushima and Chernobyl, the magnitude of the release was unknown at the time when it happened. And we need atmospheric modeling and monitoring data, and then what we call inverse modeling methods. We need that to assess the outcome. And and for that we need data, and data policy, I think, is an issue that I hope we can discuss here in this conference and find improvements yeah, so thank you.
Thank you very much for the interesting presentations. Are there any questions? Are there any questions from the web? Okay. Anyone here in the room is welcome to approach the speakers after the conference. And as I mentioned before, there are 2 interview rooms available. Thank you all for coming. And thank you.